Solving inequations, basically two steps. This technique can be used for any type of inequation. Find those critical points, that's what I was talking about yesterday. Find the critical points, or the boundaries if you like, of the solution by simply solving the equation rather than the inequation. So the equation works out when it's equal. There's your boundary. Then you simply test the regions between those critical points to see whether those points are included or not. Simplest type we look at would be the linear ones. I don't know, when did we start looking at those? Year 8, something like that. Solve it like a normal equation, but remember the key thing. You change the sign when you multiply or divide by a negative number, or as I like to think about it, if you change the sign, you change the sign. Okay, change the sign of the number, you change the sign of the inequality. Then we moved on to quadratic inequations and polynomials in general. So something like this: 6 minus 5x minus x squared is greater than 0. So what I'm saying is you would solve it like it is an equation, not an inequation. What would we do? We would factorise. Mind you, I find it easier to factorise positive x squared rather than negative x squared. So I've done that, but I've changed the sign. So if I change the sign, I change the sign. Factorise it. Now that gets me my critical points. My two solutions are 1 and negative 6. I'll draw myself a little picture and test a point. Let's test, 0 is always easy. If we sub 0 into that, we get 6 is bigger than 0. Yes, it is. So I know I'm in between minus 6 and 1. So the thing with quadratic inequations, you're always going to be either between the 2 points or on the outside of the 2 points. It's going to be one of those two things. So there's my solution. X is in between minus 6 and 1. Absolute value inequations. Remember the definition of an absolute value. The actual definition is this. The absolute value of A is A when A is greater than or equal to 0, but it's negative A when A is less than 0. So in other words, the absolute value of A can be two things. It can be A or it can be negative A. But when we get something like this, the absolute value is greater than or equal to 1, then either 3x plus 2 is greater than or equal to 1, or the negative of 3x plus 2 is greater than or equal to 1. So it's either positive or it's negative. Solve each of those individually, brings out the critical points, negative 1 and negative a third. Well, it's already telling me which way, but if I'm unsure, I can still test a point anyway and see where we are. But we're looking at less than negative 1, but greater than negative a third. So x is less than or equal to negative 1, or x is greater than or equal to negative a third. Pronumerals in the denominator. This sort of one. Draw out your critical points. Bottom of the fraction can't equal 0. That creates a critical point. I get x equals negative 3. Solve it like it's an equation, not an inequation. I get x equals negative 13 on 5. Draws out the two critical points. I can now test, and actually it's the same one as we did yesterday, isn't it? But just using a different method. We end up on the outside of the 2 points for this one. The interesting thing about these two is they can actually be turned into quadratic inequations. It's another way of doing them. So absolute value, if I was to square both sides, the inequation will be preserved. So I could turn this into 3x plus 2 squared, because it doesn't matter whether 3x plus 2, remember I said there's two possibilities, either the positive of 3x plus 2 or the negative. But if I square it, I'm going to get the same answer. Square 2, you get 4. Square negative 2, you get 4. So if I square both sides, I know I'm okay. It becomes a quadratic equation. My critical points, and, well, I didn't bother drawing the graph this time because we've already found the solution, but we get those same critical points, we know we're on the outside. The pronumeral in the denominator one, again, this is a technique I know people love doing. Square the denominator. Why do you multiply by the denominator squared? Because then you can ensure it's a positive number that you're multiplying by. Therefore, the sign does not change. So you multiply. Now, if you do use this method, I personally don't, but if you do use this method, do not expand out. Because when you draw it to the other side, you've already got a common factor of x plus 3 because of this technique. So leave it factorised like that and say, hey, they've got a common factor of x plus 3, leaving me with 5x plus 13. And again, it's the same one we did before. We know that's the solution. Let's have a look at the extension 1 HSC from last year. This was the pronumeral in the denominator question. X on 2x is greater than or equal to 5. Here's the way we looked at yesterday. Yet another approach. Let's move everything to the left-hand side, turn it into one fraction. Now, yesterday I said, oh, the top could bring out the critical point for the x-intercepts, the bottom would bring out the critical point for the asymptotes. Here's yet another way of thinking about these questions. To be honest, not a huge fan of this, but it is another way of thinking about it. So if this fraction is positive, then the numerator and the denominator must have the same sign. So the first case is if they're both positive. If they're both positive, 6x minus 10 is greater than 0 and 2 minus x is greater than 0 as well. So that gives us two possibilities. X is greater than or equal to 5 on 3 and x is less than 2. But both have to be true. Therefore, the solution to this case is x is in between 5 on 3 and 2. The other possibility is, of course, they're both negative. So if they're both negative, we end up with the possibility that x is less than or equal to 5 on 3 and x is greater than 2. Well, 5 on 3 is 1 2/3, so it's impossible to find a number that is both less than 1 2/3 but also greater than 2, so this case has no solutions. So overall there is only one solution, and that is x is in between 5 on 3 and 2. Again, as I say, not a huge fan of thinking about it that way, but it is another way you could think about that type of inequation. And graphs. Graphs can solve inequations. If you've got an accurate graph, and that's, I guess, the big problem with this technique. See, when we solve this, left-hand side minus right-hand side is greater than 0, what we basically are saying is, if I was to draw the graph y equals that, when is it above the line y equals 0? So if I was to look at the picture, when is it above the axis? Well, you can use the same idea. If you've got any function greater than another function, what you're really saying is, on my picture, when is fx above gx? If I had to do this, absolute value of 5x minus 3 is greater than x plus 2. There are the two graphs, and what we're really saying is, when is that absolute value graph above that straight line? And this is where being an accurate graph is important, because you want these points of intersection. If it's nice and neat and it lands on the grids, beautiful, I can read off the graph. Otherwise, I'm going to have to solve this equation. So let me solve it. Again, two possibilities. The absolute value could be the positive of 5x minus 3. That gets me x equals 5 on 4. Or it could be the negative of 5x minus 3, which is, of course, 3 minus 5x. That gets me x equals 1/6. But all I've essentially done is found the critical point, so why did I really need the graph anyway? So good if it's nice, neat points and you've got an accurate graph. If you don't, well, you may as well just solve it as an equation. Looking at our graph, I now know what those x values are, and I'm saying, well, when is the absolute value graph above the line? So it must be on the left-hand side of 1/6 and on the right-hand side of 5 on 4. So I can use the graph. Of course, if you're using it not necessarily in an exam, and you've got a graphing package like Desmos, then it becomes a better option because you can zoom in and get the exact value quite quickly on graphing packages. Okay, that shall do us for today.